Okay, well, we are at 1 minute after the hour, so let's go ahead and get started. Welcome to the Air-Sea Fluxes from Space webinar series. Today we have Shannon Brown from JPL, who's going to talk about progress toward a space-based air-sea heat flux mission, Butterfly to CIMR-Flux. So for people who saw the title and wondered what this is about, this is really an effort to get turbulent air-sea heat fluxes from satellite by combining multiple satellites. But Shannon's going to explain all of this. So take it away, please.
Sure. So thank you, Sarah, for inviting me to talk here, and thanks for everyone for joining this morning or afternoon, wherever you happen to may be. Yeah, just introduce myself briefly. Yeah, Shannon Brown. I'm here at the Jet Propulsion Laboratory. I supervise the passive microwave instrument science group. So we work with the science community and the technology community to develop passive microwave radiometer systems to advance both the science of earth science, planetary science, heliophysics, what have you, as well as advancing the technology and then matching those two to kind of make progress. And today I'll be focusing on one of my favorite subjects, which is ocean science, atmospheric science, and the combination of those two, air-sea heat flux, something we've been working on for a little while with many on the team here. So let me bring up my presentation here. Ready? Okay.
Looks good.
Oh, all right. So first, I'd like to acknowledge a number on the butterfly team. I'll list the names of everyone else towards the end of the presentation, but acknowledge a lot of contributions here from this previous mission called Butterfly, which I'll talk about, and also the ESA Simmer team. So this is something that we've been working on for a little while now. Actually, it's getting close to a decade now since we first started thinking about it, and kind of give you an update on where things are at and kind of appeal for some community support here towards the end of this. So I'm sure I don't have to dwell too much on this with this group. Let's see if I can get this thing out of the way here. There's not anything blocking the top of the screen here, is there?
No, yeah, it's probably just for you.
Yeah, just for
And you
me.
may be
Okay,
able
just wanted
to
to make
hit a
sure.
couple dots and make it go away.
There we go. Now it's gone away. Okay, so yeah, probably don't have to dwell too much on the importance of air-sea flux for this group here, but it's one of the things that has been looked at as a kind of a critical thing for improving longer range weather prediction capability. There's been a lot of papers recently that have shown that small-scale air-sea heat fluxes, particularly in the mid-latitudes, some even in the tropics, but in the mid-latitudes, in the western boundary currents, really kind of drive the global weather patterns, the setup of the planetary scale waves, which can significantly impact weather on long time scales. We've sort of seen that this year with the setup with the west coast of the U.S. being very dry, the east coast being very cold, because you just have these ridges that just set up and remain very stable. And air sea fluxes may be key to kind of understanding how those get set up and how they break down. Uh, there's been a lot of work recently on looking at very high resolution coupled ocean atmosphere models that have shown promise for improving longer term predictability when you have the atmosphere and the ocean talking to each other. One example of that is also relevant to where we're at here in Southern California is atmospheric rivers. Most of our rain in Los Angeles in particular comes from these atmospheric river events, which can just be over a few days, but dump a whole season's worth of rain. And that sort of happened here in December, right around New Year. And there's been some work showing that if you have coupled models, you can get forecast improvement out to long to medium range. There was a paper showing you can get 12% improvement in water vapor content, which is important when that hits orography, say in California, how much rain gets dumped. And there's also been some papers showing that there's a that having this coupled model can not only improve or increase the number of errors that get predicted in models, but also shows that there's a significant intensity increase when you couple models. And there's also this kind of remote effect where, say, one storm or one atmospheric river event coming across, say, the Kuroshio or the Gulf Stream can kind of precondition the environment for subsequent ones. So if you increase the instability, so that a subsequent storm coming over the same western boundary current will have enhanced moisture flux into the storm, enhanced heat into the storm, which then intensifies it, collimates the water even more, and then leads to about 4 to 5 days out a stronger atmospheric river than would otherwise have been present. So it's this that these air sea fluxes that we think can, as we make progress in coupled models and our understanding, that can make a big difference. However, the issue is that we don't really have any well, we have observing systems that can measure air sea flux, but they have limitations, they have advantages. So of the two main methods is in situ methods. These are buoys, sail drones, ships, and these are very accurate direct flux measurements. So in situ measurements are going to be an important part of any observing system. There's no doubt about that. But the problem is they're point measurements, and you can't really observe mesoscale spatial structure. But they're going to be our most accurate method for understanding flux, and again, important part of an observing system. Now, satellite methods. Now here you use since there is not really an air sea flux observing system. People have taken kind of combination of heterogeneous satellite measurements. So this could be, say, surface temperature from one sensor, winds from another sensor, um, uh, air sea temperature difference from a model, and combine these, and that allows you to produce a flux product and gives you global coverage and modest spatial resolution on the order of 50 to 100, a couple hundred kilometers. But the problem is when you do that combination of measurements, there are, well, you're combining things that are at different accuracies, different spatial resolutions, measured at different times. And particularly as you go toward smaller and smaller spatial scales, as the atmosphere decorrelates much faster at these scales, you start getting very significant errors. So if we are wanting to push down to these small spatial scales, which is important for, we think, making advances in improving longer term predictability, we need to have a measurement system that is dedicated to getting to these small spatial scales. And just to illustrate that, the plot here on the left, there's two columns. The left, kind of the middle column here, is the modeled latent heat flux gradient at 0.125 degree resolution. And then on the far right is modeled sensible heat flux gradient at 0.125 degree resolution. And this is the northern Gulf Stream. Now, the middle two plots here show the same thing, but when the wind speed was offset from the other fields by several hours. And this would be the case if you were trying to combine, say, an IR data set with an IR SST data set with a scatterometer wind data set, for example. And you can see that the field gets distorted, blurred out a little bit because wind shift SSTs evolve in time, particularly at small spatial scales. And the structure gets distorted. You're getting fairly significant flux gradient errors in this case. And then the bottom plot here shows similar situation when you use lower resolution measurements, which would be an example if you were trying to use microwave SSTs, which are on the order of 60 kilometers. These are half degree inputs here. And again, because of the very highly nonlinear structure of the gradients and the latent and sensible heat flux fields, you're really not resolving the true magnitude of the total flux into the storm because you're missing all of this small scale high flux structure. It's just getting completely washed out. And then the plot on the left here gives a real world example of this situation. The colored line is CFlux product version 3. And then the kind of upside down triangles are from a ship. And you can see that there's sort of a general correlation between the two. This is across the Gulf Stream. But as you get toward kind of higher flux side of this, you can see errors greater than 100 watts per meter squared. So this is quite significant, and really just because you're um, trying to make the best with what is available. There again, there isn't an air-sea flux mission at present. And this is just one more example showing high resolution total flux, so sum of latent and sensible heat flux. Again, in the northern Gulf Stream, northern Atlantic region off the coast of US and Canada here, where you can see very high regions. This is associated as a cold front kind of passing over the Gulf Stream. Um, Total flux is on the order of a couple hundred watts, 700 up to 700 watts per meter squared. And if you just do something simple like in this model, offset the wind field or all of the atmospheric variables from the surface variables, which is kind of a common situation when you're trying to merge satellite data. Just doing that, even if all the measurements were perfect, just the time decorrelation alone would result in hundreds, up to 200 watts per meter squared of error. So when you get down to these small spatial scales, simultaneity is key. And that's what led to back in 2016, we started having some discussions about an air-sea flux mission with Shell Gentiman. That there's really a need for this, and we have the capability and technology to do it. So this was something that we started putting together a small team and developed for a NASA Earth Ventures 3 mission that was called Butterfly. Now, this was submitted through COVID, which was an adventure in itself. I'm sure all the teams that worked on any of these Earth Venture mission proposals can fondly recall that time in their lives. But it was very well received. It received a Category A ranking as a part of the NASA EVM3 process, which means it's technically ready, scientifically compelling. However, it was among four of those that were also technically ready and scientifically compelling. And no fault of its own or any of the others, it wasn't selected. There was another mission, a precipitation mission, which was an equally fine mission called ANCUS, that was selected. So it unfortunately didn't make it through this round, but that doesn't mean we stop and we keep moving. And one other thing I want to bring up is that and this was something that Shell was a big proponent of, is that Butterfly was the first really fully open science, as far as I'm aware, the one proposal that really embraced open science. It didn't just say it was an open science proposal; it actually did in action. So this is something that made a lot of people nervous. But the one thing that Shell was a strong proponent of was if we're going to be open science, let's put the proposal out on online for anyone to view. So anyone can go. Now, it's not the full proposal. There's other things that aren't included, but at least the science section is included at this link here, and anyone can go and read it. And I think this is a theme that we want to continue forward as this kind of mission concept evolves. That we want to retain this open science because it is important, and we've heard feedback from a lot of particularly early career investigators that really want to get into developing missions, understanding how the process works. That's a good resource to go. So I encourage anyone to go and look at that and get it's a way to get involved. Now, how do you measure flux from space? So this is kind of the meat of the concept behind Butterfly is if you're going to get down to these small spatial scales, as I showed, you really need to have simultaneous observations of wind forcing, air sea temperature, and humidity difference. And there's a lot of sensors that can make these measurements, but a passive microwave radiometer system in particular is ideal because it can make all of these measurements with a single sensor. You don't need to combine various sensors, and that makes it nice for a kind of a small, compact, low-cost mission. And it works in clear and cloudy conditions. So an infrared instrument would be another solution for, say, high resolution SST. However, it doesn't can't measure in clouds, which in these storm regions, as these areas are crossing, say, the western boundary currents, a lot of the areas of highest flux are associated with clouds. So that could be an issue. And they also don't provide wind measurements. So the microwave instrument is a passive microwave instrument is really ideal. Um, However, the issue is that no system, no microwave system has ever flown that does this. There's been systems that can measure atmospheric parameters, systems that measure near surface parameters, like surface temperature, winds, and so forth. But the combination of the two hasn't been flown before. And the reason for that is let's take a look at the information content in the microwave spectrum here. So currently today we have microwave radiometer systems that are flying from 1 gigahertz all the way above 200 gigahertz up. Actually, there's some flying up in the terahertz region, but I'll focus here on 1 gigahertz to 200 gigahertz. So on our current sensors don't measure a whole lot of the spectrum, about 8% or so. And the sensors, as I mentioned, are really only designed for looking at atmospheric parameters or looking at surface parameters. And the primary reason for that is if you look at the spectrum here on the left side of the spectrum, so towards the lower frequencies, 1 to 20 gigahertz, let's say, there, the atmosphere is transparent, so you're primarily looking at surface properties. So this is looking at dielectric and temperature changes of the surface, from which you can infer things like sea surface salinity, surface temperature, the wind vector over the ocean surface. As you move towards the right side here of the plot, higher frequencies, here you're starting to see the atmosphere is becoming more opaque. You're seeing absorbing from gases. Water vapor and oxygen are the main absorbing gases in the troposphere and the stratosphere for lower stratosphere for in the microwave region. So there's a line around 22 gigahertz, which is the small bump kind of in the middle of the plot there. And then there's a bunch of lines around 50 to 60 gigahertz and 118 gigahertz. These are oxygen lines that you can measure temperature with because it's well mixed in the atmosphere. And then there's a strong line around 183 gigahertz for water vapor. In between these strong atmospheric absorption lines, the signal there is transitioning from kind of originating in the mid to upper troposphere to originating from near the surface. And it's in these regions, kind of on the shoulders of the absorption lines, where not really many of our sensors operate today. That's where all the information is about the near surface air temperature and humidity. Now, the reason why these haven't really been combined before is kind of a practical reason, and that is for the spatial resolution of a given sensor. These are fraction limited optics, so that means your spatial resolution is the reflector diameter divided by the wavelength. So on the right side of the plot here, you can get a perfectly acceptable, scientifically compelling spatial resolution of, let's say, 15 to 30 kilometers with a very small antenna. So this would be a reflector on the size of 15 to 30 centimeters. If you go all the way on the left side, this is where you need to get the sea surface temperature. You need to have a reflector in the order of 3 to 6 meters. And the technologies that allow you to put a 3 to 6 meter reflector into space, um, um, they work well at low frequencies, but they're not at all compatible with a high frequency system. So it's more of a practical thing that these two kind of sides of the spectrum just haven't been combined into a single instrument before, and also just because the communities historically have been a little bit separated, where you had an atmospheric modeling community, an observation community, and an ocean monitoring and observation community. There hasn't really been until now a really strong need to bring those together, but as our models move toward coupled models, we need coupled observing systems. So that was kind of the motivation, original motivation behind the Butterfly mission. So that's how Butterfly works. So this is uh, um, the concept, the original concept behind Butterfly was you're going to combine on a small sat using a lot of technology that's been developed over the past couple decades, NASA and other places, that allows us to kind of shrink these the receiver system down at least, so that the power and the size, the mass are all compatible with a small satellite. However, you can't really shrink the reflector down all that much unless you go to more exotic methods. But you're combining a low frequency system that gives you that surface information, sea surface temperature and wind vector, with a high frequency system that's optimized for measuring near surface air temperature and humidity. And the way that we did this in practice with the butterfly mission is we just divided the two systems up, where the low frequency system went on the zenith deck of the spacecraft, and the high frequency system went on the low or the nadir deck of the spacecraft. And that was a very workable solution. So this both of these reflectors had the same spatial resolution, and they were conically imaging, which gave you about a 640-kilometer swath at 400 kilometers altitude. And I'll get a little bit more into that here in a bit, but that was a compromise that we had to make. So this was how a butterfly worked, and we did some simulations leading up to the proposal and published some papers on this concept several years ago. So getting back to that plot I showed earlier of the WRF model flux, again, the top plot here showing the model. And then the butterfly would be if you incorporate all of the sensor errors, all of the algorithm errors from the measurement, simulating the flux over this, measuring the flux over the scene. This is what you would get with butterfly, was the bottom plot. And then the right-hand side, the bottom right-hand side here shows the model minus butterfly. So you can see the errors on the order of less than about 50 watts per meter squared at the most. And then just to give you an idea of the coverage, because the one of the areas where the microwave measurement won't be able to get access to the surface is in areas of intense precipitation, and that's denoted here by these kind of black pixels here, which would be essentially flagged data in practice. So that kind of gives you an idea that even though precipitation is associated with some of these storms, it doesn't really block your view of the kind of the total flux that is associated with these events. And you're doing much better than if you were just to combine even perfect measurements made at different times. So overall, this is a significant, represents a significant improvement just due to the simultaneity and the fact that the sensor was designed particularly to make these measurements. And these were the requirements that we had set and the predicted performance. Again, this was from the butterfly proposal. We had set requirements of better than 13 watts per meter squared, or 13% for latent heat flux, and 14 watts per meter squared, or 23% for sensible heat flux. And our detailed simulations showed that we could meet these requirements. The colored, the blue and the red line here are the predicted performance for latent sensible heat flux. So that's kind of the accuracy that we were expecting to get out of the sensor. Now, we had to make several compromises when we uh, tried to fit in the EVM cost cap, and these are realities that kind of hit hard when they first happen, but in the end you get over them. But this is something very typical as you go through any mission development. We start out with a very ambitious scientific vision, and then we run into the wall of implementation realities. And our original concept, which was called FluxSat, which in fact no one liked that name, and that's why it eventually got renamed Butterfly. But anyway, that was a similar small set to what ultimately ended up being Butterfly, but it had a much larger reflector, a 3-meter deployable reflector. Both the high frequency and low frequency were going to give on the order of 10 to 15 kilometer spatial resolution. So that was what we originally wanted to get to. But the problem was the EVM-3 has a cost cap of $200 million. That means you're not buying a $60 to $80 million launch vehicle. So you have to go on a shared ride. That reduces your available launch volume because you have to now pack it into, say, these ESPA rings, which are just rings that sit on the bottom of a launch vehicle that allow you to kind of put the sensor around like kind of ornaments on a Christmas tree. And also every mechanical deployment costs money, and low TRL components, like in this case, well, deployable reflectors now are a little bit more mature than they were back when we did this. But still, that any kind of deployment like this, particularly on a small cost cap mission, adds risk. So that really drove us to a solid reflector that wasn't deployable. And what this meant for the butterfly mission was it was still scientifically compelling, but not as compelling as we originally wanted, which was the resolution was limited to 25 kilometers. We needed to fly low to even get that spatial resolution because the wavelengths that we're working at down at 6 gigahertz are so long. And that reduced the swath width. Again, it was still a viable mission, but it was smaller than we wanted. There were also some field of view blockages, the way that when we had to place the high frequency reflector on the bottom when you put real spacecraft structure in there. I was just saying in general, overall, the cost, the total cost of the mission was driven by the accommodation of this very large low frequency reflector on top of the spacecraft. It drove the cost of the spacecraft, it drove the cost of the payload, and that was kind of a big driver. So now that brings me to a completely separate mission, which is independent of Butterfly, which is CIMR. It's the Copernicus Imaging Microwave Radiometer. This is a ESA mission, and what it does is it's part of the EU Copernicus expansion program, and it's primarily a polar mission, although it will do a lot more than that. And it's um, one of its main contribution is looking at very high resolution sea ice concentration in the Arctic. And one of the main requirements was no hole at the pole, which demands a certain swath width close to about 2,000 kilometers, which gives you very good coverage. And it also demands the sea ice requirements demanded very high spatial resolution. So if you want a wide swath and high spatial resolution, and this mission is a surface mission, so it's low frequencies, you need a very large reflector. So with this is not an understatement at all. CIMR is a very large and ambitious mission. It has a reflector, if anyone's familiar with the NASA SMAP mission, which is a soil moisture and salinity mission. This reflector is even larger than SMAP. SMAP was 6 meters. This is closer to 8 meters. It's actually 7.4. And whereas SMAP included just one frequency, 1.4 gigahertz for salinity and soil moisture, CIMR has essentially all the channels that you would want for a low frequency imager that range from 1.4 to 37 gigahertz. So it has CNX band channels, 7 and 10 gigahertz. These give you SST, sea surface temperature. And then 10, 18, and 37 gigahertz, these channels give you, and they're also fully polarimetric, so they give you wind vector. So this is a very compelling mission, has a very wide swath, and it's going to provide, when it launches in sometime in 2030s, provide sea surface temperature globally daily, 15-kilometer spatial resolution, and wind vector, depending on what collection of channels that you use, on the order of 5 to 15 kilometers, and then a number of other parameters that this list isn't exhaustive. There's a lot of parameters here, but the main message here is this is an ESA mission that's going forward that is making these measurements. And the other key piece is not only is the spatial resolution good, but the uncertainty is also on par with what we kind of the state of the art for microwave retrievals of wind speed, better than a meter per second, and sea surface temperature about zero point 0.2 degrees C. So not only is it giving high resolution measurements, it is also promising to give very accurate measurements, as well as these other parameters, sea ice concentration, salinity, soil moisture, and so forth. Now, how this matches with Butterfly is getting back to the limitations that we had to make when we were putting together the Butterfly mission, is they were really all limitations associated with the low frequency system, which is giving you that surface information, temperature, and wind. And that was where all of the cost drivers were too. So with CIMR, because this is a NISA mission that is going forward, um, it's taking care of all of that, that giving you all of that information. So it's a very natural partnership to kind of reconceive this butterfly mission into something that we're calling CIMR-Flux. And again, I think like FluxSat, this name will eventually get made better because I don't think anyone likes it, but it's what we're calling it for now. So you can instead of flying both the low frequency system and the high frequency system on one small satellite, you can just pull off the high frequency system, put it on its own small dedicated satellite, which isn't going to be all that big, on the order of maybe less than a kind of a meter cubed type size for the spacecraft here, relative to SIMR. That's pretty small, and have this as a free flyer that flies with CIMR. So going along, CIMR is providing the surface information. The sensor is providing the near surface air atmospheric information. The combination of those two now allows you to measure the latent and sensible heat flux, which you couldn't do with either system alone. But together, it's a very cost-effective and scientifically compelling way to get this measurement. So the way it would work in practice, so this is something that we've been working on here for the past couple of years, JPL and with ESA, is that the two systems are programmatically decoupled. When you talk about kind of international collaboration, if you have a very coupled collaboration, things get a little bit more challenging. NISAR was an example of a very coupled collaboration where kind of two independent organizations were working on the same instrument. Here, you have a collaboration, except it's programmatically decoupled, where SIMR is kind of on its own time frame, and then this companion sensor, which is there to measure the near surface air properties, can be on its own time frame. It can kind of just join the train whenever it's ready, and that makes for much easier partnerships to develop. So the sensor would fly in the same orbit plane, kind of maintaining a certain distance behind SIMR. And we're looking at less than about 3 minutes separation. That's not for the flux, the simultaneity of the flux measurement. That's more for getting the widest swath width for the effective flux product as possible. Every minute of separation between the two satellites would result in about 30 kilometers of reduced swath width. So we kind of set an arbitrary bound on that we don't want to lose more than about 100 kilometers of swath, effective swath. So that kind of sets a 3 minute separation, but that's kind of not a very hard and fast requirement. And it's also these two measurements are asynchronous. They don't have to coordinate at all in space. All of the coordination is done on the ground. You resample the two products, one from SIMR, one from this high frequency small set, to produce the Flux product. And they'll have very similar observation geometry, so it's very straightforward to do that. So that's the concept that's in development, and just comparing these two. So it's one of these things where Butterfly didn't get selected, but maybe that turned out to be an okay thing, because now with this new concept, we're in every aspect, it's an improvement over what we were trying to do with the Butterfly Earth Venture mission proposal. Spatial resolution is going to go from 25 kilometers down to 15 kilometers. This was getting to our original goal with that kind of unachievable original FluxSat concept. The swath is going to go from 640 kilometers to 1900 kilometers. This will give us daily coverage. It'll give us the complete picture as we fly over storms. We're not going to kind of chop off the left side or the right side of a storm. The uncertainty we're keeping the same. But what this doesn't mean the sensor has to stay the same, because we're going to a higher spatial resolution. We do need reduced uncertainty in the radiometer, so we have ways to deal with that. But the goal is to keep the product uncertainty the same. The mission duration, the Earth Ventures are shorter missions. So we had promised 1.5 years for Butterfly. SIMR, at least the ESA side, is confirmed for two sensors launched at 5 year intervals. That gives at least a decade of SIMR observations. If you were to have the high frequency instrument there for that same amount of time, you would have a decade of flux observations. And then the cost is also a big advantage. Where Butterfly, we were hitting that $200 million EVM cost cap mission. Here, you're trying to do something much less ambitious. It's just a much smaller system. less requirements, less hardware. This is something that we feel can be done for less than about $50 million. And note the caveat down there in the quarter. And then this would, that the costs here, not the simmer cost, that's a whole different animal. But these were the cost of just adding the component, the flux component to it. In rough terms, this would be a lower cost way to do this measurement, gives the same accuracy at better spatial resolution over a longer time period and over a wider swath. So overall, a win in every category. So the the radiometer system, just a little bit of details on that. The current working concept. It's a free flyer version of the sensor that we had originally proposed on the butterfly mission, but incorporates the latest and greatest technology, which has evolved. Technology is evolving very rapidly now, particularly in digital receiver technology. So we're incorporating the latest and greatest there in our concepts. And then there's some necessary improvements that were needed for the CIMR-Flux requirements, particularly as you get toward lower spatial resolutions. The time per pixel reduces, meaning your noise goes up. So you have to find a way to deal with that. And we can deal with that by very simply by making the receivers, instead of linear polarization, which they were for butterfly, to fully polarimetric, which gives you about a 40% noise improvement over at the sensor level over butterfly. The swath, the imaging geometry is designed to match exactly that of CIMR, same spatial resolution, same swath. The sensor, it's configured here to show to be mounted on the zenith deck, although it can be mounted on the nadir deck, and that's something that we're coordinating with our ESA partners on. There's no blockage of the imagery around the scan because we use electronic calibration sources. That improves the sampling density, which is important if you're trying to measure small mesoscale fields. We're able to do this with no new technology. It's all mature technology, high heritage designs. That's important because we want to be ready. We're in 2026 now. We want to get this up there as close as possible to the start of the CIMR-A mission, which will be in the 2030 timeframe. The main products from the sensor, the main requirements are going to be for near surface air temperature and humidity, where the SST and the winds are coming from the CIMR sensor. So the current status, as I mentioned, we're over the past 2 years have been working on this concept at the kind of programmatic and engineering level, working on putting together the mission concept in collaboration with ESA. Here at JPL, working on the instrument design, prototyping some hardware, and preparing for a mission concept review plan for 2026. Things got a little bit, let's say, delayed because of the budget uncertainty in 2025, but we look to be getting back on track now. I'll say that this is still a concept in development. Nothing's confirmed, but we are working towards this in collaboration with ESA and NASA. But there are many competing budget priorities at NASA. I'm sure everyone is aware of this. So, and a lot of compelling science missions as well. So to see a mission like this go forward, community support is something that's very important. Not only for science, but also applications. Applications are becoming even more important in the kind of the priorities going forward. So this could be related to hydrology forecasting, flood reservoir management, things like that that could come in to play. So the support could be in the form of white papers, committee recommendations, advocacy at the program manager, directorate level. The way that we see this is it's a relatively minor NASA investment would kind of lead to outsized scientific returns develop long-term partnership on this. And it would also improve the kind of the similar baseline mission as well. I won't really get into that, but that's also other things that we're looking at. And I'll just kind of put this into perspective here, this mission. Sure, you're all familiar with the Odyssey mission, which is currently in consideration for the Earth System Explorer. So CIMR-Flux and Odyssey are very complementary missions, where Odyssey is going after the momentum flux, whereas this CIMR-Flux, which is formerly butterflies, going after the heat flux, and combining these, you're kind of looking at the whole picture. So these are very complementary, and having them both up at the same time would be kind of a really a strong measurement observing system to have in space. Okay, so I'll finish here with just to say that this is a mission that that's been evolving since about 2016 when we first started talking about it. It's a very kind of exciting concept that it really gets to where we wanted to be before we started putting together the butterfly flux mission. And I'll also say that, open science does remain a key to the team, kind of the core team that's thinking about this from day to day. And think of this as a community mission. So, reach out, put a list here of people that you can contact, pick person that you know best, or reach out to me, either way. Um, and reach out with science and Earth action ideas. Earth action being applications. It could be mission themes. It could be support. You want to join the team, provide advocacy, provide compelling reasons to do the mission that we can put in front of headquarters and say, hey, this is a mission that the community wants to do. So, this is something that we can do together. So, I'll leave it at that, and happy to answer any questions or have further discussion. So, thanks for your time, and thanks, Sarah, for hosting.
Thank you very much, Shannon. Questions? This was great.
Take this down so I can see people.
I see Yolanda. Sarah has a question.
Hey,
And
yeah, great talk. Thank you so much. That's really interesting. I just had some clarifying questions. So you were mentioning in the beginning of your talk about how the time, the delay, and I know you said 6 hours, and now you're talking much less than that. But can you speak to how, if these are separate satellites, that they would pass over the same spot somewhat delayed? And I mean, you did show errors, but I'd like to understand better why that's not an issue here. Like, is it just because they're passing over so much more quickly? And you had mentioned the distance between them wasn't really as much of a concern, although you're trying to get that 100 kilometer maximum. So I don't know if you could just clarify how being on different satellites, this how that affects the errors.
Yeah, sure. So yeah, even though yeah, I talked about when you're taking, say, independent satellites in different orbit planes, they may cross over a particular, area anywhere from, hours to days apart from each other. So yeah, that when you're combining just independent satellites that aren't coordinated at all, that's where you're going to get those most significant decorrelation errors. In the case of CIMR-Flux, where they're essentially think of them flying in tandem. So the separation between the two sensors is just going to be minutes apart. So let me see if I can find a swath picture here. Maybe this one will be good enough. Um, Whoops, lost my screen here. 1 second. Okay. So actually, this is a pretty good illustration of what you would actually
I
get.
think you're not sharing screen at the moment.
Let
Yeah,
me
I lost your slides. I think now they're not shared.
let me go back here. Okay,
There we go.
get this out of the way here. Okay, so this is actually a pretty good illustration of what would actually happen with these two satellites. So they're going to be just a few minutes apart, but the swaths are going to more or less be overlapping each other. So even though this wasn't meant to illustrate that, I can illustrate that. So think of this kind of this first swath here. So the microwave radiometer is flying along, it's tracing out an arc, and as that arc traces along, it makes an image on the surface. So let's see. Yeah, so this essentially would be some flux here. And then the next satellite is going to be flying along, making its own image. So within just a minute or so of each other, you're observing the same spot on the ground with the two different sensors. So the temporal decorrelation at minute timescales is the error from that is essentially negligible.
Okay.
The only concern is that as the Earth is rotating, when the next satellite flies over, you're kind of reducing the swath because one moves left compared to the other. Um, so that's really the only concern that would set up the time difference between the two. Does that
Oh,
clarify it?
it does. It does. Okay. And then I just have one more question like that, which is these are global coverage. So you'll get the tropics, I mean, as well as the poles. You had mentioned that the other mission, the CIMR mission, the European mission, was focused on no hole at the pole. How will the tropics be sampled, or is it, yeah, if you could just mention the difference in sampling with latitude.
Yeah, so they'll be sampled. So the entire globe will be sampled. There actually won't be any gaps in coverage. I
Okay.
don't have a coverage map in this presentation, I don't think, but there are some online that if you just type simmer,
Okay.
you can find a website on it. So
Okay.
at the polls, you're going to get coverage about 10 to 15 times per day, depending on how close you are to the pole.
Okay.
10 to 15 observations per day. In the tropics, it'll be anywhere from a half a day to a day coverage.
Okay, so once, maybe once, twice a day in the tropics, below
Yes.
40, like below 40 or
Yeah,
30.
that's right.
Mhm.
Okay, thank you so much.
Sure.
Rick Danielson in the chat asked if the 3-minute delay needs to be fixed before launch. Can it be changed after launch?
No, that's just a requirement that we placed, and we wanted to make that as loose as possible. That isn't anything that's stringent at all. So, in practice, the way this would work is, you're gonna get both sensors up there, and you're gonna get some separation that's comfortable enough for everyone for orbit collision avoidance or safety. And then there's going to be station keeping that each one's going to do, and that'll how often you do that will depend on how much fuel you have and so forth. So it might vary from uh, 60 seconds to 90 seconds to 60 seconds to 90, something like that. But yeah, it's not that stringent at all. And that kind of flexibility is one thing that we want to stress because that if you do have rigid requirements, which we don't, that would drive costs and things like that. So yeah, we're trying to maintain flexibility.
Megan Cronin has asked in the chat about the time of day for coverage or measurements, but
So
particularly for the tropics or the mid-latitudes.
yeah, Simmer is in early morning orbit, 6 a.m., 6 p.m. sun sync orbit. So for and actually I think that was the same orbit that we were in for Butterfly as well. So yeah, it'll be 6 a.m., 6 p.m. sun sync observations. And obviously that's for kind of more of the equatorial regions at the poles that doesn't really matter so much.
Um, Marcos Portobello has a hand up.
Yes, hello, Shannon. Really
Hey,
nice
Marcos.
presentation. I was wondering, so I should be aware of that, but I'm not. So you mentioned there's two CIMRs now being launched 5 years apart. So I
Mhm.
guess that if they're operating fine, they're going to be flying in the same orbit, and both of them will be basically operating at the same time. So does that mean that you plan also to have two, let's say, tandem missions here, or not?
Ideally, that would be great. We're working on getting one tandem mission. So yes, um, if we succeed in getting confirmation for one tandem mission, then the extension to two tandem missions is a very small cost delta, particularly if you're building multiple sensors at the same time. So
Okay.
yes, that
And I
that is
have,
the vision.
and I have another question. This one is a bit more tricky, I guess. So you mentioned that, of course, both missions are programmatically decoupled, and that has, of course, some pros, but it also has some cons. I understand. So if you, one of course, let's say the problems we can find is that if they want to wait until maybe the mission is flying, because otherwise they say, okay, if you put, let's say, all the eggs into these fluxes, then they say, what happens if CIMR fails? Yeah, then there's no point to launch yours as satellite. So are you thinking of, let's say, to put also a lot of effort in trying to, let's say, I don't know, show all the science you can do with only this mission?
Um, we haven't put a lot of thought into that yet, although that's a good something good to think about. So, yeah, and we're still trying to remain on the optimistic side. But yeah, it's a good argument to have in your back pocket.
Yeah, yeah, okay. Thank you.
Lucy Remondet has her hand up.
Okay. Hi. Hi, my name is Lucy. I'm a PhD student at Scripps Institution of Oceanography. I was curious, so you obviously you didn't choose the orbit since CIMR sets it, and I'm curious if for the science you would have chosen another orbit, or if a dawn dusk orbit is desirable, or does that bias what you're going to measure? Can you comment on that?
Yeah, so orbit selection is always kind of a delicate balance between engineering, cost, and science. Um, we did choose the same orbit, and for butterfly, we did put some thought into it back then, and the the trade-off of going to, say, a different orbit where it has advantages. For example, a non-sun sync orbit, you can measure at different local times of day, which could be important for that. Um, the advantage, and one of the reasons why a lot of satellites, including CIMR, are in this particular orbit, is thermally and power. Uh, Power and thermal are um, lower cost to implement compared to other orbits. So I would say for any sun sync orbit, might be kind of equal in terms of their scientific um, merit, because a lot of what we're looking at uh, are, say, mid-latitude storms crossing western boundary currents, which aren't really going to have that significant of a diurnal component. Um, so in that sense, it might not matter so much, but there might be other scientific applications, particularly in the tropics, where a diurnal component becomes a little bit more important. So the way I would look at this is uh, where we are today is we don't have any kind of dedicated flux mission. Let's kind of take the steps necessary to get one up and minimize the cost to doing that as much as possible, which kind of factors into the orbit selection, an orbit that is a little bit cheaper to operate in. And then once we have that, demonstrate the utility, then we can move on to more kind of less used orbit planes that give sampling over the diurnal cycle and things like that. So yeah, that's kind of where I see things going.
Yeah, thanks.
Are there any other questions? And if not, maybe I'll wrap up. You mentioned, Shannon, um, the opportunities for the community as a whole to get involved and to voice it, to identify priorities, to articulate opportunities. Do you know what the opportunities might be for um, developing a science team that would go with this, or coordinating science among community members?
Yeah, so and this is going to be kind of an ad hoc group at the start, but we do have kind of regular discussions with kind of the people listed here on this slide. So there's always an opportunity to join some of those discussions. But at the start, it's going to have to be the community coming together to kind of a self-organization, I would say, kind of like the way any of these things develop. So that could be around um, uh, relevant scientific meetings, workshops, that type of thing. We were looking at kind of hosting a workshop sometime in 2026. So that's something to look out for, that we we may do. So yeah, I would say just stay tuned. We're trying to uh, get the momentum going this year. Coming out of 2025, things are looking a little bit better in 2026 in terms of budgets, so that we can kind of get some momentum and get towards a kind of a mission concept review. And as a big part of that will be showing the community support. So yeah, again, look out for potentially a workshop coming up. But then yeah, any type of kind of grassroots advocacy. Again, reach out to me or anyone else here, and we can build this as a community.
And maybe something that goes with that is if people have ideas that might fit into this particular webinar series is a great place to have discussions and begin to formulate some of the science opportunities and share things that are coming together.
Yeah,
So people can also reach out to the webinar organizing committee to get on the schedule or to suggest something that should be presented here.
yep.
Well, if there are no further questions, thank you so much for a really great presentation and a great discussion.
Thanks all for tuning in, and hope to talk to you some more soon.
Yeah. Thank you.
Bye now.